Welcome to the next session, my dear friends. In the previous session, we have discussed filtration, and now in this session, we are starting a new topic in treatment of water. After filtration, we do disinfection. After filtration, we do disinfection. So, what is disinfection? What is disinfection? Actually, though the filtration removes the colloidal particles and the dissolved particles and in the water, but still there will be microbial load, that is bacteria and other kinds of microorganisms will still present in water, because if you see the slow sand filter, the water which is coming out of the slow sand filter is having dissolved metallic ions, that is color causing compounds, because slow sand filter is not that effective in removal of color causing compounds. So we need to treat the color causing compounds which are present in the water coming out of the slow sand filter in the disinfection. As well as if you look at the rapid sand filter, it is not that effective in removal of the microbial load, that is microorganisms. So now for killing those microorganisms also we need disinfection. See, here in disinfection we not only take care of the microorganisms, we also take care of other kind of organic matter which is not oxidized in any of the system. Okay, so all these things, so oxidized matter will be neutralized, and also if there is any metallic ions are present which are causing color causing ions or any kind of metallic ions, if it is present, that will be neutralized, and along with that microorganisms will be killed. Okay, so the water after disinfection, it is completely free from all the impurities. Okay, so simply we can say that the water which is coming out of the disinfection is fit for drinking, except if there is any kind of miscellaneous treatments are needed, then that miscellaneous treatment we will provide either before disinfection, or if it is needed after disinfection, we will provide it after disinfection also. But majorly all the treatment process will be done before the disinfection, and at the last we will do disinfection, and then we will enter after disinfection, we will start supplying the water to the community. So that is what we do in disinfection. Okay, here so the main motto of the disinfection is to kill disease causing microorganisms and to remove or oxidize organic matter if present, and to oxidize metallic ions which are causing color. So, but disinfection, if you see, majorly many of the process in disinfection only work for this. Majorly all the disinfectants, majority of the disinfectants cannot be able to do these two tasks, but they are capable of doing these two tasks. Okay, so let us see what are those disinfectants and how they work, and why we don't use those disinfectants for the bulk water supplies and all these things we will learn. Before going into that, so disinfection can be done in two ways. One is by physical means, another thing is by chemical means. Okay, disinfection can be done by physical means and by chemical means. So disinfection by physical means disinfection can be carried out by physical as well as chemical means. So physical methods such as boiling, so treatment with UV ray, so these are some kind of physical, and chemical using KMnO4, so KMnO4 treatment, chlorine treatment, bromine treatment. So all these things, when you are adding some chemical to the water to kill the bacteria, that is called chemical treatment. If you are not adding anything, we are giving physical energy. Boiling giving heat energy, treatment with UV rays giving light energy. So if you are giving some physical forms of energy, then it is called physical means of treatment. And if you are adding some kind of chemicals, then it is called chemical treatment. Okay, then it is called chemical treatment. And now when we do either physical or chemical treatment, what happens to the microorganisms, how they will die? So what is the mechanism by which we are killing the bacteria or any kind of microorganism? What is the mechanism of disinfection? Mechanism of See, the mechanism of disinfection is mechanism of so first one is breaking of cell wall. So damaging the cell wall by damaging cell wall of microorganism. See here how skin is protecting our body. In a similar fashion, cell wall protects the body of a cell. See, because it is very small creature, very small organism. So the cell wall is plays a very major role. It protects the organism. So if you damage the cell wall, so the microorganism cannot sustain. So we do here damaging of cell wall, so by which we can kill the bacteria. That is one method. And other method is by altering the protoplasm, by damaging the protoplasm or altering the protoplasm by damaging the protoplasm. So this is present inside the cell structure, which is very important for the survival of the microorganisms. So if you kill this, if you damage this protoplasm, so it is an important organ, like important process inside the cell functioning. So now if you damage this process, then what happens? Obviously the microorganism will die. We can do like this, or we send some kind of enzymes onto the food. Okay, so microorganism is also a creature. So it is invisible. That is why we cannot see it, what it is doing and all. But it also like a creature. So whatever the creature will do in the same manner, it will also eat the organic matter and survive. So when you spray some kind of poisonous enzymes onto this organic matter, so that will enter into the system of the microorganism, by which the microorganism also dies because of those poisonous enzymes. Okay, so sending some kind of poisonous enzymes into the microorganism is one kind of killing also. Okay, so this is three methodologies which are importantly we generally prefer to disinfectant to kill the bacteria or microorganism by precipitating poisonous enzymes. So these are the three important mechanisms by which we kill the microorganism. Now, what are the different methods? See, there are some minor methods and one major method. We will discuss all the methods one by one, and what is the method where it is suitable, and what are the drawbacks of that method, making it unfit to use for mass water supply, bulk water supply. Every method we cannot use for bulk water supply. So why we cannot use for bulk water supply, that also we need to discuss. Now first one is boiling. So these are all minor methods. So first one is boiling. So we all know about this boiling, so it's not needed to explain much about this. So but here boiling means heating of water, and once you heat the water, and all the microorganisms cell walls will get damaged and they will die. Okay, now the boiling, it needs lot of energy. So here to boil water needs lot of energy, and once you cool down the water, what happens? Again, it is prone for future contamination. So once the water is brought to normal temperature, it is prone for contamination again. So So here boiling cannot take care of future contamination. So boiling cannot take care, it can't take care of future contamination. It cannot take care of future contamination. That is no residual power. So this method of disinfection does not have any residual power which takes care of future contamination, and boiling of bulk water so needs lot of energy. So boiling of bulk water which is sufficient, which is necessary to supply, needs lot of energy, needs lot of energy, and hence it is uneconomical, and hence it is uneconomical. So boiling is not economical as it needs lot of energy, and also there is no future contamination for contamination controlling capacity. So contamination cannot be prevented. So that is why it is not having a behavior of ideal disinfectant. An ideal disinfectant should be cheap and it should take care of future contamination. It should be powerful disinfectant. It can be storable. So there are some kind of criteria of ideal disinfectants. We will discuss it later. So this is one disinfecting method which is over. Minor methods, boiling is over. Next is UV ray treatment. UV ray. See, UV rays, what they will do, generally UV rays will have a different wavelength. It is having a wavelength of 240 to 260 nanometer. Okay. So with this wavelength, generally UV rays if comes on to our body also, it is risky for us. Too much of exposure of UV rays may also damage our skin and also our health also. That is why, so prolonged exposure of UV ray kills the bacteria or any other kind of microorganisms also. A prolonged exposure to the UV ray will kill the bacteria. So UV treatment. UV treatment. So the wavelength of UV ray is 240 to 260 nanometers. So because of this wavelength, it is a very powerful, which is because of this wavelength, it acts as a powerful disinfectant. So it also damages the cell wall of the bacteria or microorganism, and it kills it when it is in contact with this UV ray. So there will be a UV chamber, big UV chamber will be present. In this UV chamber, you will send the water, and that will kill all the bacteria or microorganism present inside the water. So here the thing is, problem here is, can we construct that much big UV chambers that can be capable of treating bulk water supply? So that is a big question. So that is one problem. And another problem is, once the water leaves the UV chamber, then there is no more residual UV ray which is traveling along with the water, so that it can take care of future contamination. So UV ray, when the water is inside the UV chamber, when the UV rays are passing through the water, then the water is disinfected by this UV rays. Once this leaves the UV chamber, then the water is prone for future contamination. There is no residual capacity. That means immediately after coming out of the UV chamber, we need to consume the water. Otherwise, the water is prone for disinfection. Now, how can we consume all the water at a time? We need to store some water also for the demands, to meet the variations in the demand. So that is why generally this is not suitable for bulk water supply. Rather, it is suitable for hospital dispensaries and some kind of institutions, cinema theaters and all. So in those locations where we directly consume the water, there UV plant will be small UV kind of arrangement they do. So that water directly we consume into our body, so that water is okay, which is coming out of the UV chamber directly. Otherwise, it is not fit for bulk water supply or municipal water supply. Okay. Here the water is bulk water needs to be sent into a big UV chamber which is practically uneconomical, So if you look at UV treatment, it does not need any material. Simply there will be a light ray. Okay. So the construction of UV chamber needs money and maintenance is nominal. But here there will be UV light rays, there will be lights which emits the UV rays, okay, which emits the UV rays. So here we don't need any kind of material. So that is why it is economical. Actually it is economical. The problem here is it has no residual capacity. That is why we are not using it, okay. So here I am writing uneconomical because construction of that much big UV chamber is uneconomical. But treatment is very cheap. And so the water coming out of UV chamber can be contaminated again. So hence there is no residual capacity. Hence there is no residual capacity. So that is why we don't use this UV treatment for bulk water supply. So the rate of disinfection using the dose, that means if you know the dose of the UV ray, is nothing but what is the intensity of the UV ray and what is the duration, contact time of water with the UV ray intensity. How much time you have kept the water in contact with the UV ray, that means inside the UV chamber. That is what the dosage of UV ray. If you know the dosage of UV ray, so we can find the number of organisms being killed and number of organisms are present inside the water. So number of organisms remain in water, number of organisms remain in water at a time t is ln nt by n naught. Ln nt by n naught is equal to minus k I into t, or it is also called minus k into d. What is nt? Nt is number of microorganisms present after a time t. Number of microorganisms present after present in water after time t. N naught is initial concentration. Initial concentration of microorganism in water. Initial concentration of microorganism in water. K is the rate constant. Rate constant means nothing but the slope of the degrading graph. See, whenever it is happening, how we have derived this? See, initially the microorganisms is N naught. Okay, these many microorganisms are there. When you are increasing the time of contact of water with the UV ray, then what happens? This will reduces like this. So it's somewhere, if you take at t, this is nt at some time t, at some time t. Okay, this is nt. So nt, I am finding nt. Nt is the number of microorganisms present in the water after the time t. So whatever the this slope of this graph is nothing but k, rate constant. The slope of this graph is nothing but the rate constant. Okay, this is I is the rate constant. Sorry, k is the rate constant. I is intensity of UV ray. I is the intensity of UV radiation. Intensity of UV radiation in microwatt per centimeter square. In microwatt per centimeter square. And T is the time of exposure. T is time of exposure. Either in second or in minute. Either or second in minute. So this product of these two, I and T. So D is nothing but dose is equal to product of I and T. Sometimes they won't give you the intensity and the time of exposure or time of contact. They will directly give you the doses of the UV radiation. Dosage is nothing but the product of I and T. The product of I and T. So I and T is nothing but microwatt per second centimeter square. Okay, this is nothing but the doses. This exposure is nothing but time of exposure or time of contact also. We can call it as time of contact also. Okay, so likewise we can find the number of microorganisms that are present. Number of microorganisms that are present inside the water after a contact time of T with a intensity of I, with an intensity of UV radiation of I, that we can find easily. Okay, so this is all about UV radiation. This is all about UV radiation. Next is treatment with excess lime. Treatment with excess lime. Treatment with excess lime. So here generally how we survive within a pH range, that means when we consume water we need a pH range of 6.5 to 8.5 for our survival. Okay, generally this is the limit of pH in which we can consume the water. If this pH is greater than 10 or greater than 9, then it is harmful to us, isn't it? It is harmful to us. Similarly, in the same manner, pH greater than 9.4. So when pH is greater than 9.4, then microorganism cannot sustain at this pH. Microorganism cannot sustain. Okay, cannot sustain. So that means here why I am telling this is, when you are adding lime, it increases the pH, because lime is nothing but alkaline. Lime is having alkaline nature. So here addition of lime excess lime, addition of excess lime increases the pH of water to such an extent where microorganism cannot survive, cannot sustain. So that is pH should be increased more than 9.4 where microorganism cannot sustain. So now what happens is, so if you keep this pH like this, humans also cannot sustain. We also die when we drink this water. So that is why what we need to do, so once the treatment is over, once the killing of bacteria is over, so we need to reduce the pH. Okay. So the pH needs to be brought to the normal range to supply water, supply of water. But during this process, so now what we are doing, we are adding lime to the water. Now we are inducing impurity into the water, which is not needed for us. We are adding lime into the water, and again that lime we are removing using some other method. So to bring back this pH again to the normal level, so that means drinkable level, pH that is 6.5 to 8.5, we need to add carbonation. That means we need to add some kind of acid to it. So we are adding alkalinity to the water, and again to reduce the pH by sending carbonic acid or CO2, by sending CO2 that is carbonation. So when the CO2 goes through this water, so this lime will react with CO2 and forms a precipitate of CaCO3. Calcium carbonate precipitate will form. That means, so when after carbonation lime reacts with CO2 and forms CaCO3 precipitate Now, so after the treatment, whatever the precipitate is formed, this is nothing but a sludge. Again, we need to send this water into filter to remove this precipitate. So that means we are adding some impurity into the water, and again to remove this impurity we are adding another impurity into the water. Again these two are removed in the form of a precipitate. Again this is another impurity. Disposal of this is again a big task for us. So all these things, if you look at the treatment, so the lime treatment is cheaper, economical, and we can easily store lime, and no technical supervision is also not that much is needed. But the problem is sludge disposal. So more amount of sludge will form. Disposal of sludge is a big problem here. It creates more sludge disposal when use it for municipal supplies. So that is why generally we don't prefer this method. For bulk water supplies. This is treatment with excess lime. Next is, now these days we all know that sanitizers and hand wash, everything we are using, so which kills bacteria or virus or whatever it may be, what kind of microorganism is present, that will kill the microorganism. These are called surfactants. That means it will act on the surfaces. We call them as surfactants, like soap, water, hand wash, soap water, sanitizer, phenols, phenol based sanitizer, alcohol based sanitizers. So all those things are surfactant. We call them as surfactants. But when you add this surfactant to water, it deteriorates the quality of water. Next is surfactants. So surface active chemicals. These are surface active chemicals can kill microorganisms in water, but they deteriorates, that is damages the quality of water. So whatever the water which is added by this soap water, can we drink soap water? Yes, soap water, bacteria, soap can kill the bacteria, but how can we consume that soap water? Can we? No. So that is why the surfactants may be effective disinfectants, but not at all fit for drinking water purposes. Okay. Next is treatment with ozone. Start it. See, ozone will be having a nascent oxygen. That means ozone, generally O2 is the stable form of oxygen. So O3 is unstable form of oxygen. Treatment with ozone. So in the ozone, generally we will be having a nascent oxygen. So O2, so when O3 is present, O3 will disintegrates into O2. So 2O3, O2 plus nascent oxygen. So this nascent oxygen is having it is a very powerful disinfectant. See, whenever you see, the disinfectants will be powerful only when they are highly unstable. The disinfectants are very powerful only when they are very highly unstable, or when they are having greater affinity to get the noble gas configuration. See, I will tell you later what is the affinity, and what is the instability. Here in this case, nascent oxygen is unstable, that is why it is very powerful disinfectant. Okay, if you look at chlorine, fluorine, bromine, iodine, these are halogens. So these are powerful affinity is there for them. They are having powerful affinity. So what is affinity? What is stability? We will discuss now. Stability means it needs one more oxygen to get a stability, molecular stability. Again, oxygen will have affinity, but it is molecularly stable. It can exist in the form of O2. But if it gets some carbon in its vicinity, then attracting to the carbon is affinity. Okay, this stability means existing like O2. So this oxygen will exist in a molecular form of O2, that is stability. When O2 reacts with the carbon and forms CO2, so there O2 is having affinity to carbon. O2 is having affinity to carbon, that is why it is reacting with carbon and forms carbon dioxide. So that is the affinity and stability. Here it is unstable. So due to this instability, it is very powerful disinfectant, very powerful disinfectant. So disinfecting with the ozone. So ozone disinfection is called ozonization. So disinfection using ozone is called ozonization. Ozonization. And we cannot store this ozone, as O2, O3 is highly unstable, so we cannot store it. So O3 is highly unstable, and hence we cannot store it. So the ozone quantity which is needed for the treatment, we will generate it at that time and we will use it. So whatever the quantity of ozone needed, we need to generate it. So the O3 required for disinfection is generated at the spot, is generated whenever it is needed, in ozone generators. There will be ozone generators which generates the ozone upon the requirement. So how we generate is by sending the O2 and air. So in ozone generator there will be electrical current. We pass the O2 and air through an electrical field. So we send the O2 and air through an electrical field. This is electrical field. So in this ozone generator, so this O2 and air combines and it gives an output of O3. So generally 1 kg of ozone requires 0.826 kilowatt hour power. So 1 kg of ozone, 1 kg ozone generation needs 0.826 kilowatt hour power. So this much of power is needed. power is needed. So that is why ozone generation, the ozone manufacturing is very costly. Where ozone manufacturing needs a lot of money. So if this is the only for 1 kg ozone, then for bulk water supply on daily basis, how much ozone is needed, then what should be the cost of the water. So generally the normal dosage of ozone in water, normal dosage it is varying from 2 to 3 mg per liter, 2 to 3 ppm or mg per liter. So we can add more ozone to have a residual capacity. Here ozone is capable to prevent future contamination. Ozone is capable of taking care of future contamination but as it is highly unstable, it cannot sustain till the supply of water. It cannot sustain till the supply of water. See, so we have added ozone to take care of future contamination in the disinfection procedure. In the disinfection procedure, you have added more than the requirement. You have added more than the requirement of ozone, so that the ozone will present in the water, which will take care of the future contamination up to its consumption. But as I told you, ozone is highly unstable. So though you keep it more than the required amount of the dose, it will not sustain for longer duration. So you think that there will be residual capacity to the water, but if ozone present, then there will be residual capacity to the water. If ozone reacts, then ozone is not present, then how the residual capacity will come? So generally, if the residue is present, then ozone can also take care of future contamination. And to find whether the residual ozone present or not, we perform a test, orthotolidine test. We call that test as orthotolidine test. Okay, residual ozone in water is determined by a test called orthotolidine test. Orthotolidine test. So using this orthotolidine test, we can measure the residue of ozone. Residual ozone we can determine. Okay. So this is all about the ozone treatment, and we are left with some other treatment processes, that is treatment with KMnO4 and treatment with major treatment which we perform, that is Cl2, and there are some kind of halogen group chemicals along with Cl2, that is bromine, iodine also helps in disinfection, and also some kind of metallic electrodes also helps in metallic ions also helps in disinfection. All those things we will learn in the next class. Thank you so much.